So in the previous video, we discussed how to do a test on a single proportion. And in this video, we're going to discuss how to do a test on a single mean. So first of all, let's take a look at example 10.9. So I will give you about a minute to read through the problem. You can pause this video. Okay, time's up. So this problem gives us a lot of information. So it's a problem related to the actual average distance that the phone works. Okay, so we're gonna first of all let mu be the actual average distance that the phone works, and we also let x be the activation time. Why did we have such assumptions? Because in this problem it says if the distribution of activation time is normal with standard deviation is equal to 1.5 degrees. Okay, so this means my x follows a normal distribution with mu and sigma squares, where sigma is equal to 1.5. Okay, and here we're interested in this mu. Okay, so what else? We also know that the sample size is equal to 9, right? N is equal to 9, and a sample average is equal to 131.08. Okay, so which means my x bar is equal to this stuff. Okay, so in the beginning of the problem, it also says the claims says the true average system activation temperature is 130 degrees. So my claim is mu is equal to 130. So does the data contradict the manufacturer's claim at significance level alpha is equal to 0.01? So it means, so this one versus mu is not equal to this one, right? Remember, how do we set up an appropriate hypothesis? First of all, you set up the claim, right? And then you write down its opposite side. Then you find where the equal sign here. So this one would be your null hypothesis, and its opposite side should be your alternative hypothesis. So here for this test, my null hypothesis is mu is equal to 130 versus the alternative hypothesis is mu is not equal to 130. Okay? So after setting up the null hypothesis, we need to find the corresponding sample statistic with respect to this parameter of interest, mu. Okay, so we can use x bar here. Okay, and this x bar, in general, it should follow a normal distribution with mu and sigma square divided by n. When the sample size, remember, when n is large, if your sample size n is not large, say larger than 30, it's not larger than 30, you cannot have such conclusion. But this problem says, although the sample size is 9, so the sample size is not large, okay? So you cannot apply this one. But it says my x, so the distribution of activation time is normal, which means the original distribution is normal. Okay, if the original distribution is normal, then its sample size, its sample mean is also normal, right? It's also normal. So you can still have this conclusion, even if your n is equal to 9. It's not that large, right? Because the original distribution or the underlying distribution is normal. Okay, then we can find the z statistic, right? Because we know that x follows a normal distribution. So we can have my z is equal to x bar minus expectation divided by the standard deviation, right? So minus mu divided by sigma divided by square root of n follows a normal distribution. Okay, and then because my null hypothesis is mu is equal to 130, right? So you plug in this mu 0, okay, mu 0, and the sigma is known, is 1.5, and this n is also known, and it's equal to 9. So this value can be known. right? So Z observed is known. Okay, then we need to figure out the rejection region. Okay, so it's pretty similar to the previous example about the the proportion, right? Because here we are still using this Z, and my alternative hypothesis is mu is not equal to mu 0. So the corresponding rejection region should be Z is larger than Z alpha divided by 2, or Z is smaller than Z alpha divided by 2. Or you can write in this way, Z is larger than Z alpha divided by 2. Okay, so which is, alpha is 5%, so let me see, alpha is 0.01, so alpha is 1%. Okay, so alpha divided by 2 should be 0.005. So you can find this critical value from the Z table. Okay, so it's 0.58. All right, and then after calculating my observed Z, this is equal to 2.16. And my rejection region is Z is larger than 2.58, or Z is smaller than negative 2.58. Okay, and you compare whether this value falls into the rejection region. So this would be negative 2.58, positive 2.58. Okay, and Z observed is here, 2.16. So it does not fall into the rejection region. So not within the rejection region. So we fail to reject the null hypothesis. Okay? So we fail to reject the null hypothesis. The data does not give strong support to the claim that the true average differs from the design value of 130. Okay? We can also use the p-value method to solve this problem. Remember, the p-value method is the probability. The p-value is the probability of obtaining the observed sample, or more extreme, given the condition that the null hypothesis is true. Here, our null hypothesis is mu is equal to 130 versus the alternative hypothesis is mu is not equal to 130. And we also have that x bar, which is the sample statistics that we have observed, is equal to 131.08 degrees. Okay? So because our alternative hypothesis is mu is not equal to 130, so that means it's a two-tailed test. And these areas should be equal because they're symmetric, right? And each area is equal to alpha divided by 2. Okay, so in this case, your p-value of this two-tailed test should be 2 times the p-value of a one-tailed test, okay, because they're symmetric. Here, I'm going to use this side as my example. So Z is smaller than Z alpha divided by 2, negative alpha divided by 2. Okay, and you double this, so which is the p-value of the two-tailed test. So this is equal to 0.0154. So the final answer is 0.0308. And you compare this p-value to the existing alpha. Okay, so if the stated alpha is equal to 0.01 in this problem, okay, so you're gonna compare this p-value to this alpha. So in this case, this is larger than this alpha, so you fail to reject the null hypothesis, which has the same conclusion as what we did using the rejection region method. Okay? Okay, so example 10.10, and I will give you 1 minute to read through the question. You can pause the video if you want. Okay, time's up. So in this problem, we're interested in the average height of American adult male. So it is believed that this mu should be equal to 69. So this is our claim. Okay, and the question is, do we have enough evidence to say that this mu should be greater than 69 inches? And definitely, using the rule that we discussed before, my null hypothesis should be mu is equal to 69 inches versus its alternative hypothesis is mu is greater than 69 inches. Okay, so that's my hypothesis. In order to test this hypothesis, I have to set up my test statistic. Again, we're going to start from the point estimator of this mu. So it's going to be x bar, right? So in this problem, it says assume a researcher randomly select 50 men. So our sample size is 50. And the average height is 61. And the standard deviation is 2.45 inches. So here, because the average height and the sample and the standard deviation are from the sample, so it means these two are sample statistics, especially the second one. Okay, so a lot of people would think this one is the population standard deviation. It is not. Okay, it's from the sample. So it's the sample standard deviation. So it uses as here. Okay, so as the sample standard deviation is equal to 2.45. Again, I'm gonna use this x bar to construct a distribution, but in this case we cannot construct a z anymore because we do not know the population standard deviation. Remember in chapter 9 we used t distribution instead of z when the population variance or the population standard deviation is unknown. Okay, so I'm going to use t. So t is equal to x bar minus mu divided by s divided by square root of n. So this one follows a t distribution with degrees of freedom is equal to n minus 1, right? Because we have n is equal to 50. Okay, so this degrees of freedom should be 49, right? Okay, so like it says, step 2, we specify the test statistic. Okay, so t statistic is equal to x bar minus mu divided by s divided by square root of n. All right, and we know that my null hypothesis is mu is equal to mu0 is equal to 69 inches. So you plug in the value of mu0 here, and s is known, n is also known. So you can have your t statistic here. This one follows a t distribution with degrees of freedom is equal to 49. Okay. Again, because our alternative hypothesis is mu is larger than 69, so your corresponding rejection region should be t is larger than t alpha n minus 1. Okay, why is that? Remember in chapter 8 and 9, we learned the PDF of t should be like this. It's symmetric with respect to 0. It's pretty like the standard normal distribution, but it also has a degrees of freedom. So when the degrees of freedom t distribution goes to infinity, so t distribution is the same as z distribution. Okay, but here it's not. Here is degrees of freedom is equal to 49. Okay, so when your alternative hypothesis is the parameter of interest is larger than something, so the rejection region will be like this. Okay, so you let this part be equal to alpha, the probability that t is larger than t alpha and minus 1. Okay, so this is the critical value. So you're gonna use the value alpha to find this critical value in the in the t table. Okay, so in the t table, when alpha is equal to 5% and degrees of freedom is equal to 49, you're going to find this t value is approximately equal to 1.676. All right. Then in step 3, you calculate the observed t statistic and make conclusion. Because this is our t statistic, right? And my x bar is equal to 71. So mu0, s, and square root of n are known. So this value is known, is equal to 5.77. And you compare to the critical value. So this is the critical value, okay, 1.676. So because this one is larger than this one, so it falls in the rejection region, and we reject the null hypothesis, which means there is strong evidence that the average height of American adult male should be greater than 69 inches. Again, we can use the p-value method to solve this, okay? So because this is alternative hypothesis, is mu is larger than mu 0, so it's a one-tailed test, okay? So your p-value is the probability given the null hypothesis is true, which is mu is equal to 130, okay? And the probability of obtaining the observed result, which is 71, or goes extreme, which means it goes to this direction, right? So your x bar should be larger or equal to x bar observed. Okay, so this is x bar is larger or equal to 71, given mu is equal to 130, right? And then we convert this x bar to t. So x bar minus mu divided by s divided by square root of n is larger than 71 minus mu divided by the same thing. Okay, you plug in this mu is equal to 130. Okay, so which is my t is larger or equal to, so if you calculate this one, it's equal to 5.77. Okay, then you can calculate the corresponding probability using the t-table. So this one is smaller than 0.0005, which is very small. Okay, and because we have stated that our alpha is equal to 5%. Okay, so this one, this p-value is much smaller than 0.05. So we reject the null hypothesis and support the alternative hypothesis, which has the same conclusion as the rejection region method. Okay. All right, so in general, there are three different tests about a population mean, which is mu. Okay, so they share the same null hypothesis, but they have different alternative hypotheses. So mu could be larger than mu 0, mu could be smaller than mu 0, or mu is not equal to mu 0. So the first two are one-tailed test, like before. Okay, so this is a two-tailed test. Since we're interested in the population mean, mu, so I'm going to find its corresponding point estimator, that is x bar, right? And I'm going to use the distribution of x bar to construct a new distribution, which is z distribution or t distribution. So which distribution to use depends on the information of the population standard deviation. If the population standard deviation sigma is known, then you can use z distribution, right? Because z distribution is equal to x bar minus mu divided by this one. So if this is known, you can construct your z, okay? But if it's not known, I'm going to use the sample standard deviation to replace this sigma, okay? So I'm going to use t instead of z. So because t is equal to s divided by n. So this one follows a t distribution with degrees of freedom n minus 1, where n is the sample size. Okay? So when sigma is known, we use z-test. Okay? And the corresponding rejection region for mu is larger than mu 0 is z is larger than z alpha. The rejection region for mu is smaller than mu 0 is z is smaller than negative z alpha. When mu is not equal to mu 0, so the corresponding rejection region is the absolute value of z is larger than z alpha divided by 2. Okay? So if sigma is unknown to us, like we discussed before, we're going to use t. Okay? So if your null hypothesis is mu is larger than mu 0, the rejection region is t is larger than t alpha n minus 1. If your alternative hypothesis is smaller than mu 0, so this one will be smaller than negative t alpha n minus 1. If your alternative hypothesis is mu is not equal to mu 0, your rejection region will be the absolute value of t is larger than the critical value. Of course, here your alpha should be alpha divided by 2 because it's a two-tailed test, right? And the summation of these two areas should be equal to alpha, and they're symmetric. So each area should be alpha divided by 2. Okay? All right, so that's all for the test on a single mean. Okay, so example 10.11. So like before, I'm going to give you about a minute to read through the problem. So you can pause the video if you want. Okay, time's up. So in this problem, a manufacturer claims that a new design for a portable phone has increased the range to 150 feet, allowing many customers to use the phone throughout their homes and yards. And the question is there evidence that the manufacturer's claim is false? So first of all, we're going to define what's the primary interest in this question. Okay, so I will let mu be the actual average distance that the phone works. Okay, so my null hypothesis could be mu is equal to 150. Okay, so what about the alternative hypothesis? So the question is there evidence that the manufacturer's claim is false? So some people would say, okay, so in this case, my alternative hypothesis is mu is not equal to 150. Well, it sounds reasonable. However, if you read through the first sentence, we're discussing the average rate of the signal. Okay, so if the range of the signal is large enough, like people could use phone throughout their homes and yards. Okay, so in this case, your alternative hypothesis is more reasonable to be mu is smaller than this range. Okay, if it's larger than this range, then people can use it, right? So the purpose is to use it. So my alternative hypothesis is mu is smaller than this one, so they cannot use it. Okay, so this is my hypothesis. So what else can we obtain from this problem? We also have, they draw a sample, and the sample size is 44, right? So the sample gives the average distance of 142 feet with a standard deviation of 12 feet. Again, this standard deviation means the sample standard deviation because it's drawn from the sample. Okay, so we have x bar is equal to 142 and s is equal to 12. Okay, so this is my first step, set up an appropriate hypothesis. So the second step is to find the test statistic, right? Because the population parameter of interest is mu, so we can use its corresponding point estimator, x bar, to construct my test statistic. Okay, so x bar can be converted to z or t in our course. Okay, but in this case, sigma, the population variance, is unknown, right? It didn't appear in the problem. However, we know that the sample standard deviation is 12, right? It's 12. Okay, so we're going to use t here. So we're going to convert x bar to t using this formula. Okay, so this one follows a t distribution with degrees of freedom n minus 1. That is because our n is equal to 44. Okay, so this one is 43. Okay, and using T, we have the corresponding rejection region. Because our alternative hypothesis is mu is smaller than mu0. So my rejection region should be T is smaller than negative T alpha n minus 1. So that is, this is negative T 0.05, 43. Okay, so if you check the T table, this is about negative 2.423. Okay, then we compute the observed T statistic, okay, by plugging the value of x bar. Okay, so x bar, observe, minus mu divided by this one is equal to, because my x bar, here what you have observed is that x bar is equal to 142. So 142 minus mu is equal to 150 divided by s is equal to 12, n is equal to 44. So this one is equal to negative 4.42. Okay, so which means T observed is smaller than negative 2.423, this value. Okay, so it falls into the rejection region. Falls in the rejection region, right? So we have the conclusion that we reject the null hypothesis, that the manufacturer's claim is false. Okay. So that's for question 2, or question B. Okay, so question C. If we change the significance level to alpha is equal to 0.05, will your conclusion change or not? Explain the reasoning. Okay, so in this case, so they should be A, B, and C. Okay, so in this case, the value of alpha has been changed, right? So this one will be changed. Okay, so my rejection region will be T is smaller than negative T alpha n minus 1. So in this case, it should be 0.05. Oh, sorry, in the previous one, this should be 0.01, okay? 0.01, but the answer is correct. Okay, so in this case, it should be 0.05, and n minus 1 is equal to 43. Okay, so if you check the T table, this one should be negative 1.684. Okay, negative 1.684. And then you compare the T observed. So this T observed will not be changed, right? So it has no relationship with alpha. So this one is equal to negative 4.42, which is smaller than negative 1.684. So still, still, which falls in the rejection region. So again, we still reject the null hypothesis. Our conclusion won't change.